to look at deductive reasoning today. Why? Well, because it's part of geometry, that's why. It's also because you do it all the time. It's another one of those things that you're totally familiar with. You just don't think about it very much. In fact, most of this particular section and a lot of this chapter, it's just a matter of analyzing the things that you probably do every day. You're, in a sense, examining your day-to-day life. Who was that philosopher? Some guy said, an unexamined life is not worth living. Yeah, I bet he got invited to a lot of parties. Hey, let's invite that unexamined life guy. He sounds like a hoot. Well, that's what we're doing here. We're just examining what you probably do every day. It's called deductive reasoning. If you're not at all familiar with it, then I recommend Sherlock Holmes. You'll learn a lot about deductive reasoning when you read his books. Actually, he's the main character. It was written by Conan Doyle. Sherlock Holmes is just the detective in the story. What is deductive reasoning? Well, the easiest way to remember it, I'll give you a definition, but the easiest way I think to remember it is analyze if it's inductive reasoning. Remember, inductive reasoning is when you just take a bunch of particular examples and then jump to a conclusion. Inductive reasoning is usually not a proof. You're just taking a bunch of examples and then making a leap from those examples. You may be 100% correct. If you're holding something in your hand, you open your hand and it falls. You can perform that experiment quite a few times. And eventually, through inductive reasoning, having seen these particular examples, you will say, if I'm holding something in my hand and I open my hand, it will fall. And you'll be right. But that's not really a proof. It's just what you're really saying is, this is what happens every time I try it. So I'm just going to assume this is what's always going to happen. It may not be true. For instance, have you ever noticed little children learn that they have a lot of power over adults, even though they can't talk? All they have to do is smile and wave their hand, and an adult will smile and wave his hand. And they start doing that. It's like pushing buttons. It goes in those department stores where you can put your hand on the little outline of a palm, and it runs the electric train inside the window. Well, they're kind of doing the same thing. They smile and wave, and it makes the adult or even the teenager smile and wave. They're obviously concluding that because so far, every time I smile and wave, the other person smiles and waves. So it will happen every time. But there may come a time that they'll just run into a not very friendly person. They'll smile and wave, and that person may just stare at them. It's not a proof. But in the absence of proof, it's pretty much how humans learn about and discover their environment. So inductive reasoning is very important. And the easiest way, as I say, when you're trying to determine whether you're looking at deductive or inductive reasoning, just decide if it is inductive. If it isn't, then it's deductive. You've only got two choices. Kind of like ordinary Western logic itself. It's binary. You got two ways to go. Not three, two. We don't have true, false, and something else. We just have true and false. The actual definition, which you've probably already read, you should have, involves using facts, definitions, accepted properties, the laws of logic, the guy sitting next to you, anything you can find to form a logical argument. Grab the kitchen sink if it helps. Whatever helps you make a logical argument. You use it and you're deducing, or you're engaged in deducement. I don't think that's really a word. Better not put that on any papers. So what's one of our laws? We have rules for deductive reasoning. Why not? This is math. We have rules for everything. The Law of Detachment. It's also called the Law of Direct Argument. I'm going to put it in symbols. What it says is, if we have a statement, P implies Q. And the truth value of this statement is positive. In other words, the statement is true. The whole statement is true. And the hypothesis is true. The law of detachment says that this has to be true. There's no way for the hypothesis to be true, the conclusion to be true, the hypothesis to be true, and the statement to be true, and then the conclusion turn out to be false. See, that can't happen. If this is true, and the whole statement is true, then the conclusion must be true. It's a law. And we'll apply it in some problems. And then we have the law of syllogism, which I prefer to call the chain rule, and other people do too. And again, in symbols, and this is why I call it the chain rule. I think you'll see how it works. It's a lot like another rule that I'll show you. P implies Q. And the and symbol there. Q implies R. Now these two statements together also form an implication or a conclusion. In other words, we could have written if P then Q and if Q then R, it follows that. If P then R. But naturally, this is a math class, so let's use the shorthand. P implies R. If P implies Q and Q implies R, then P implies R. In other words, we can just make this jump. Boom. That remind you of anything? Remember something like if A equals B and B equals C, then A equals C. That was our chain rule. This works exactly the same way. We can cut out the middleman here and just write A equals C. That's syllogism or the chain rule. I like the chain rule because it seems so much like the chain rule up here. Now here we're going to use the law of detachment. To make a statement about this statement. We're going to say something about this. For instance, in this one, if we use our P implies Q format, we have the measure of angle A is 90 degrees. If the measure of an angle is 90 degrees, then it is a right angle. So this part is P. That's our hypothesis. And the statement is that P implies Q, that it is a right angle. And this over here, we'll call this Q. And this part is P. The measure of angle A is 90 degrees. So now we have a true statement. We know that's true. We know that the statement is true. So Q must be true. Q was, then it is a right angle. So in fact, it must be a right angle. Pretty deep stuff here, right? But it's good to practice because you'll see it on a standardized exam, and you don't want to waste time on stuff like this, pondering what they might mean. These are easy. These are ducks. So you do a lot of these, and you get quick, easy credit when you whip through these on your standardized exam. X equals 12, so that's your P here, your hypothesis. Then minus X is less than minus 12. That's your conclusion. Now, is P true? Well, over here they give you the value of X, which is greater than 15, pardon me, which is 15, which is greater than 12. So P is true, the statement is true, and that means Q must be true. So we can say minus X is less than minus 12. If a book is a biography, then it is a non-fiction. I bet you know the answer to this without me even saying anything. Here's P, book is a biography. Here's Q, you are reading a biography. So that means this part here, that the book is a biography, this must be true. The statement is true. Therefore, Q must also be true. Pretty easy. Now here, we're going to use the chain rule to find out what's true, and maybe what isn't true. Let's find out. Y is greater than 0. Then 2y is greater than 0. So, and if 2y is greater than 0, then 2y minus 5 is not equal to minus 5. So, what do we conclude? Remember, we've got this part here. These should turn out to look the same. If they don't, you've got a problem with respect to the chain rule, because the chain rule says if this, then this, and if also this, then this, then if the first one, then the third one. If number 1, then number 2. If number 2, then number 3. So if number 1, then number 3. If A, then B. If B, then C. It follows if A, then C. So, what true statement can we make? Well, the statement is y greater than 0 implies 2y minus 5 does not equal minus 5. Pretty simple. All you have to do is just pull this one out. Like I said, you just get rid of the middleman and go straight from there to there. If you play the clarinet, then you play a woodwind instrument. If you play a woodwind instrument, then you are a musician. Okay, here's in our A implies B and B implies C chain. Here's B. Here's A, you play the clarinet. And here's C, you are a musician. All you have to do is make the jump from A to C. If you play the clarinet, then you are a musician. That would be the statement. Easy, right? You won't have any trouble with this stuff. And here's another easy one. We're going to use the Law of Detachment, or direct argument. Two angles are vertical angles. So that's our hypothesis, that's P. Then they have the same measure. Okay, that's Q. And here we are given that A and B are vertical angles. That's the same as saying we're given that P is true. The statement is true. That means our conclusion, Q, must be true. That is just the law of detachment, or direct argument. They have the same measure. Well, which one of these says they have the same measure? That would be this one, wouldn't it? Well, there you are. Once again, but you didn't sweat at all figuring this one out. This is an instructive problem, and it's not a common mistake among students. It's a common mistake amongst everybody in the world, bar none. If two angles are a linear pair, then they are supplementary angles. That's true. C and D are supplementary, so they must be a linear pair. Well, if if we were to call this, in fact, I'm going to call this the hypothesis, P, two angles are a linear pair. That is the hypothesis. Then they are supplementary. That's Q. What does this statement down here really say? Angles C and D are supplementary. Well, that's what our conclusion was down here, and so the angles are a linear pair. That was our hypothesis. So what they've really done is turned this implication into this one. In other words, what they have done is taken this conditional and tried to turn it into a biconditional by saying that it goes both ways. P implies Q and Q implies P. No, there's nothing in here that says so that the converse must be true. Nothing at all. So you can't say this. If you could put these together and you would have that, the biconditional. But we have nothing here to indicate that this is biconditional, that it holds in both directions. This isn't true, which means this isn't true. Or at least we don't know that this is true. There's nothing in here that says this is true. And in fact, it isn't. Now, using the laws of logic, in this case I would say deduction, what kind of a true statement can you make about this? Well, like I said, you're probably already good at this, you just didn't know it. If you save $2,000, then you can buy a car. So, this is P. And this is Q. Now, we're going to say that the statement is evaluated to true. Okay, that's fine. So we have P implies Q. And that evaluates as true. We don't know anything about P and Q yet, though. You have saved $1,200, not $2,000. That means P is false. And remember, if the hypothesis is false, the statement ends up evaluating as true no matter what the conclusion turns out to be. I know that seems strange, but well, that's one of the problems starting out with a false hypothesis. It's like an erroneous assumption. When you make an erroneous assumption, well, all bets are off because you're just dealing with bad data. So your conclusion, of course, is that you can't buy a car. That would be the true statement. And like I said, if you didn't already know that, you're probably that squirrel who snuck into the room just because you thought it was funny. And now you're confused. Otherwise, I'm sure you didn't have a bit of problem with this. Now here's one of those where they ask you, are you using deductive or inductive reasoning when you conclude that your neighbor is going to come ask you for a favor on the 4th of July? Well, last year, he or she, oh, it's a her, okay, she asked you to feed her hamster. The year before that, she went on vacation and asked you to feed her hamster. And every single year before that. Well, that's just a whole bunch of particular cases. This year she did it, next year, next year, next year. You've taken all these examples and come to the conclusion that the 6th year will be just like the first 5. And she's going to come by and ask you to feed her hamster, which means that's like 6 years now. Do hamsters live that long? Well, I guess they probably live longer if you feed them. Maybe that's what I've been doing wrong. Anyway, this is pretty simple. You can see it was inductive reasoning that they used to do this. So you can stop right there. Like I said, I always look for induction first because it's an easy one to spot. And if it turns out it wasn't inductive, then it must have been deductive. It always seemed to me like an easier way to make that determination if you need to. Here's one that's a nice example. Comes straight out of literature. It's from a poem called That. You pronounce it. I'm not even going to try. And we're going to use the law of syllogism. This will be pretty easy. We're just going to apply the law of syllogism, or the chain rule, more than once. That's allowed. Let's call this want of a nail, for instance. In other words, the property of a missing nail. We'll call that P. An hypothesis. The shoe is lost. Okay. P implies Q. Now, down here we have that Q implies, I'm going to call that R. Q is the shoe is lost. And here, want of a shoe, the shoe is lost. I would say that they have the same meaning. They both imply the property of shoeless. So we got our shoeless Joe horse here, our nailless shoe here, and our horseless rider over here. And what are we going to call this? Horse is lost. We called that R, didn't we? So rider is lost, we'll call that S. So what we have here is that P implies Q. And down here we have that Q implies R. And over here we have that R implies S. Why do I do stuff like this? Because it's a lot easier than rewriting all this verbiage. That's why. And that's why mathematicians do it too. There was a time when people did not say things like, if A equals B, then A plus C equals B plus C. Euclid would have said, if equals be added to equals, result yields equals. And that's kind of clumsy. It just doesn't roll off the tongue the way the other one does. But all this symbolic stuff started later, luckily for us. So if you don't like math, count your blessings. If this was 2,000 years ago, it would be even worse. One application of the chain rule here would lead us to P implies R. Our next application of the chain rule combining these two P implies R. However, we know that R implies S, don't we? So we can use this statement with this application of the chain rule to apply the chain rule one more time. Remove the middleman, and we have P implies S, which means that for want of a nail, come all the way down to the final conclusion. The writer is lost. This is a little tale about the importance of details, I believe. Joseph Conrad did a lot of that. I'm sure you got his books in your library. I highly recommend him. He writes really good sea stories and lots of stuff. His stories used to point out things like this, where a sailor is being washed overboard. Another sailor can only save him if he grabs the towel that is supposed to be hanging in one particular spot. He doesn't have time to look and see if the towel is actually there. He just puts his hand where the towel is supposed to be, grabs it, flips the other end to the man going overboard. He grabs the end of the towel, and the sailor is saved. Why? Because the towel was where it was supposed to be. Tiny little detail like that, and it saves a man's life. Conrad wrote a lot of stuff like that. It has absolutely nothing to do with what we're doing. Sorry. Now in these, what we're going to do is determine the truth value of these various conclusions. If these are conclusions, then this whole thing here is the hypothesis. We take it all together as a statement. we're going to assume that these statements are true. We just have to figure out if these are. In other words, using deduction, do these follow from the above statements? If Arlo goes to the baseball game, he will buy a hot dog. If the game is sold out, then they will go. Down here, if the game is not sold out. Down here it says the game is not sold out, which means Arlo and Mia did go to the game. And if he goes to the game, he will buy a hot dog. So we can make that little chain. The game is not sold out, then Arlo and Mia will go to the game. Well, the game wasn't sold out, so we have that the hypothesis here is true, the statement is true, so this part must be true. They will go to the game. And if he goes to the game, he buys a hot dog. We put that all together and we can conclude that poor old Arlo is now living on hot dogs. Too bad for him. Now Arlo and Mia went to the game. Well, I think we concluded that earlier, but let's double check. If the baseball game is not sold out, then Arlo and Mia will go to the game. The game is not sold out. This condition has been met. So this follows. That one's true. Mia bought a hot dog. Well, if Arlo goes to the game, he'll buy a hot dog. If Mia goes to the game, she'll buy popcorn. Will she buy a hot dog? Well, inquiring minds are on the edge of their seat wanting to know this. And there's no way to know, so this doesn't definitely follow. She could have bought one, I guess, but there's nothing in the information here that says Mia bought a hot dog. Yeah, that's good for her. Popcorn's much healthier than hot dogs. Arlo had some of Mia's popcorn. Well, I don't see anything up here which says Mia is inclined to share her popcorn, or that Arlo is inclined to pilfer any unguarded popcorn he comes across. I'd have to say that was false, wouldn't you? Like I said, you probably knew you could have done this even before you ever took geometry. Probably years ago, somebody could have showed you this and said, come up with the right conclusions. And you would have done it. But you wouldn't have known why. That's the only difference. Now you know why. You're living an examined life now. Good for you. Well, this, as I say, is all fairly simple. You probably already know how to do it. Sometimes the simplest things generate the most questions. For instance, prove 2 + 2 = 4. That's not easy. It's an extremely simple result. Everybody knows it's true. But when you sit down and try to prove it, it's not that simple. Well, when you sit down to analyze these things that you've probably known most of your life, the analysis might lead to some questions. So I hope you have a lot of fun discussing this amongst yourself, because it's probably going to require something like that for you to really get this solidly into your head. And that's it for this topic. It's kind of a short topic, really.